Okay, welcome everybody to this month's instance of the Chalmers AI for Science seminar series. It's the final one of this term, and we're very happy to welcome Professor Julija Zavadlav from the Technical University of Munich. She did a PhD in Ljubljana in Slovenia, where she graduated in 2015. After that, she went to the ETH in Zurich, where she did a postdoc. And she was also awarded the ETH postdoctoral fellowship there. And since 2019, she's been at the Technical University in Munich, and she'll be talking a bit about the work that she's been doing there. So we are very much looking forward to your talk. Thank you for coming and engaging with all the conversations today. We're very much looking forward to your talk.
Thank you very much for this nice introduction, and thank you, Simon, for inviting me here. I'm very excited and honored to present my work here. So my talk is going to be about machine learning potentials that have basically revolutionized molecular modeling, I would say. And I will talk about how we are approaching this and what is our contribution to this field, which is really fast growing in the recent years. So before I go into this topic, I just want to acknowledge my group. This is my current group, the latest group picture on the left. And I want to particularly acknowledge the people that did the work that I will show you here today. So my former students, Stefan and Sebastian, and my current students, Michal, Weilong, that you all know, and Paul, as well as some master students, and Anton, who was temporarily with us, as well as the funding, of course, agencies. So as I said, I will talk about molecular modeling. And the first, I want to give an idea what machine learning can really did in a molecular modeling field, right? So before machine learning, we always were dealing with this trade-off between accuracy of our simulations. Molecular simulations could be molecular dynamics, could also be Monte Carlo. We mainly do molecular dynamic simulations. So you always had this accuracy efficiency trade-off where you could get very high accurate predictions using ab initio methods like density functional theory, for example. But you could only simulate maybe 100 of atoms at a time for a very short picosecond, let's say, time scales. So if you wanted to do simulations involving millions of atoms, you had to resort to atomistic models. These atomistic or so-called force fields. These are constructed, from some physical terms that, people postulated and then parameterized in some way. So it's a lower level theory, or it's basically just fixed functional forms that have some physical intuition behind it, and then parameterization of that functional form. And then accuracy, of course, is lower, but as I can say, the scaling is much better. It's linear in terms of number of particles, so you can do millions, billions, even particles. And then, of course, one can go even a scale lower and construct coarse-grained kind of models if you want to even push even further in terms of spatial temporal scales. And in these coarse-grained models, you would group particles together in these coarse-grained beats, or more generally, you would reduce some degrees of freedom in your model. And with that, you can speed up your simulation. Okay, so this is the kind of landscape where we were for 50 years, and then AI came. And what machine learning has done is that really you can now use ab initio dataset, and you can, at least in theory, push these atomistic models to the same level of accuracy as ab initio models, but retaining the computational cost, right? So you can do large-scale simulations at ab initio level accuracy, right? And you can do the same idea and transfer it one level down, right? You can use classical atomistic force fields as your data source, and then parameterize coarse-grained models, and in order to get a coarse-grained model which has the same accuracy, but it's more computationally efficient, right? Okay, so this is the big promise. Of course, this is the problems. How it works out actually then depends on a lot of key factors. So first, I want to talk about how these machine learning potentials even work and how they are constructed. So I'm keeping very high-level kind of description, right? So in machine learning potentials, what we give as an input is a configurational and chemical state of the system, this SI. And so this is a 3D information about my system. So particles, all the atoms or particles positions in 3D space. And I also tell you what kind of chemical element it is. I can add extra information, but this is not typically the case. And then I push this into a machine learning model that has some parameters, right, theta. And then at an output, I predict the potential energy, hence the name machine learning potentials, right? And so this potential energy, of course, is different for different inputs. And then I can, generalize this for any kind of different configurational chemical states in general. Okay, so if I have the potential energies, I can, with automatic differentiation, compute forces on particles. If I have forces on particles, I can run molecular dynamic simulations, or just with potential energy, I can run Monte Carlo, let's say, simulations. So now what are the critical aspects in this kind of loop, right? So the critical aspect is what kind of model we are using, what is the architecture, how am I combining this or not combining with some physics-based models, which is very fashionable lately, and what is the actual computational cost of these models, right? Because we said, yeah, we can do the same things as classical models, but it is not always the case if we are going to make this super computational costly. Then the second thing, and probably the most important part in the loop, is the data, where the data comes from, what is the accuracy, what is the broadness, what is the source, etc. And a lot of methods here, how to improve this. And then the whole training, if you want, of the method. So this model has parameters theta, and we have to optimize it or infer the parameters in some way. So whether we do optimization or inference is going to make is going to matter, and what kind of approach we are taking. So if you want to say in a machine learning fashion, what kind of loss, then I can postulate different kind of losses, and the outputs are going to be different. Okay, so the default kind of standard where 90% or 99% of the people are typically using and how it are used is that a model would be some graph neural network, which is a go-to standard these days, but it's typically short range. And there's a now current effort to also capture long range interactions. And I'll talk about this. For the data, typically people resort to density functional theory calculations, where you would, for reference structures that you create in some way, calculate the reference potential energies and the reference forces on each particle for a given structure input. And then the loss would be kind of just matching, the energies that you predict in the model and the energies that you have in your database. And you can do the same kind of mean-squared loss for the forces and maybe also for the viral. Okay, so this is the default standard. We try to, in several ways, go beyond this default standard, and I will show you what are the benefits of that. Okay, so my outline of the talk is in 4 sections. If you're going to have questions in between, we might not reach all 4. But yeah, I want to tell you something about how we are pushing accuracy, but not only using DFT data in the training loop, but also training and parameterizing these models based on the known experimental data and what is the benefit of that, and how we are doing this with our method called the diff tree. And then in the second part, I'm going to talk about how we can get to large-scale simulations, like really million atom simulations. And in order to do that, we actually have to do a lot of software development. And I will talk about our chemtrain framework and software that now enables you to actually do this. Yeah, so I want to talk about this, and also to give you some kind of reference what is possible to do today with machine learning potential, so you have some idea in mind. And then I want to talk about long-range interactions and how we are tackling those long-range interactions, in particular by combining like physics-based models with machine learning. And we do this with our method called Chelly. And in the last section, I will talk about how we can switch from optimizations to inference, and how we can parameterize this model in Bayesian kind of sense, which of course gives us uncertainties and all other nice benefits of Bayesian modeling. Okay. So to start with, I'm going to talk about first the data and the data source, and combining experimental data in our training loop. So like I said, the standard is to use simulation data, which would be reference energies and forces. But of course, this has disadvantages in the fact that the accuracy is then inherently limited by the data generating model. And of course, if we are building atomistic kind of model, then we would resort to typically DFT calculations, and then we are, we are subject to DFT functionals that will give us different, predictions. And we know that DFT in some cases can be very wrong, give us wrong predictions, right? And if we are constructing a coarse-grained level model, then we might be using classical force fields, and the accuracy of those is even worse, right? So if we are using data from simulations, then the accuracy is inherently connected to the data generating model. And it can be also very expensive to obtain, right? If we are doing DFT databases, then we can only maybe do structures which are very small, right? Below like 100 or let's say 1,000. So what is all of this meaning in the end is that we have troubles actually reproducing some kind of bulk properties, and we may not match experimental results. So to give you a concrete example, so we trained a model for machine learning potential for titanium based on the DFT reference data set. And then we tested this model on mechanical properties across some temperature range. This is all in the solid state. And what you can see is that experimental results, which are in black, are quite different than what our machine learning potential will give us, trained based on the DFT data set. So you can see that tens of gigapascals difference in mechanical properties here in shear modulus. Okay, so this is what I'm talking about. Now, what we can do, of course, is that we can, okay, this is known experimental properties and we can include this into the training loop by and then improving the accuracy of these models, right? So how do we do that? It's a bit more complicated, right? Training on DFT calculations is trivial because you are matching outputs of your model to whatever you have in the database, because you have this in your potential energies and forces in your database. Training on experimental data is much more complicated, right? So experimentally, we cannot measure energies and forces. We measure properties like mechanical properties, structural properties, binding free energies. It's something that you are familiar in these two groups, right? So, so we have observables, let's call them, right? Observables. And what we would like is we would like to match those observables with whatever our model is predicting, right? But how do we measure binding free energy in MD simulations, right? You have to run the simulation. You have to then do an assembly average or like some extra tricks, but you have to run a simulation, and then from the trajectory that you get, you calculate your observable, right? And now, in order to optimize the model is here, right? And you need to optimize this with respect to this loss. That means computing the gradient of this with respect to the model parameters, which are here, which means that you need to trace the gradient from here all the way from the end of simulations to the beginning of the simulations, right? And this, yeah, it's a bit more involved in terms of computation, right? So you can do this, right? If you have automatic differentiation and software that can do this, you can do this. So for example, JaxMD, Google did end-to-end differentiable molecular dynamics. So you can do this in principle. But in theory, like in theory, you can do it, but in practice, it's very limited what you can actually do. The problem is that you either run out of memory, and we did very basic kind of toy case where we did like one-dimensional gas particles, but like 2,000 of them, and modeled external potential, which was modeled with a neural network with 200 neurons, a very primitive toy case, right? And we were already out of memory for like 1,000 time steps or 1 picosecond. What this means is that for any kind of system that is like on a 1,000 particle kind of scale, you need to be able to observe statistically well any kind of observable that you want to train on within 1 picosecond. That's more or less nothing, right? Very limited, right? And if you can maybe avoid memory issues if you go to adjoint methods, okay? Then you don't have this problem. But then you have another problem, which is that you are prone to exploding gradient. So when this is across all fields, not in molecular dynamics, but also in fluid dynamics. In any kind of PDE that you want to differentiate through, you kind of get exploding gradients. We are all across different disciplines encountering the same kind of problem. But for us, we get like after a few thousand steps or a few picoseconds, we get gradients that are not usable anymore in training. Again, which limits you in what you can actually train on. Okay, so what we did some time ago is this differentiable trajectory reweighting method that will avoid this differentiation through the trajectory backwards, and that means that we can avoid these problems. Okay, so what we can do is we can use reweighting tricks from 20, right? And this gives these are these two equations, and this gives us actually a direct equation relating our observables here and parameters of the model. Okay, so it gives us an equation, and we can use this equation in order to compute the gradients, you see? And it gives us direct access to these gradients without differentiating backwards through the simulation. And because of that, we can compute these gradients much faster. We don't have memory issues. We don't have exploding gradient issues, and we can even reuse the trajectories because of reweighting. So now we can do something real, right? So now we can apply this to thousands of atoms, like to bigger system, bulk systems, larger systems, and also some properties that require quite a lot of sampling, right? So we tested a lot of different things. So you can reproduce structural properties like radial distribution function, angular distribution function, and stuff like this, or mechanical properties. Mechanical properties actually require quite a lot of sampling. You have to average over pressure tensors, which are very noisy. So you kind of have to run it longer. And we can also do free energies. I will show you later, okay? In principle, you could do any structural thermodynamic property, right? In practice, again, you would need to be able to observe it. So you cannot, train on folding pathways. So, okay, but to give you a reference scale, right? Good. So that's a positive, now a negative. So training only on experimental data, and if this data is scarce, so for example, we trained a model of titanium here just on mechanical properties at room temperature. These are like 4 numbers that you train on, and your model is super complex. It's a graph neural network, 300,000 parameters, okay? So, of course, then the models become under constraints, right? So if you have scarce data, you have under constraint models, and also experimental data is not errorless. But the scarcity, I guess, it's a bigger issue here. In that, so if you train the model like 5 different times, and then to reproduce some experimental properties like mechanical properties for diamond, and then you would measure phonon density of states, you get 5 completely different results, right? So this is what I mean, it's under constraint. So the next thing is basically obvious, is that you combine the 2 data sources, right? You can do data fusion quite easily. So you can use DFT kind of simulation data and experimental data and train on both together. And now what you do is, here I'm showing you mechanical properties. So this is the bulk modulus, shield modulus, Poisson ratio, as well as lattice constants at different, like across temperature profiles. And I'm showing you the results for different kind of models. So one in black is experimental reference, which you almost don't see because the green and the blue lines are almost directly on top of it. And this is when you combine these 2 data sources. Whereas the red, the only training on a DFT kind of data set is always off, right? So the 2 combinations, you can do different kind of combinations. You can train this sequentially or together. But in general, we found not a huge difference between the 2. Okay, so obviously, if we add experimental data in the loop, we will reproduce this data. That this is a target property, right? So yeah.
Sorry, it might be tangential, but you say the red data, for example, is really bad. But I think it's remarkable that it reproduces the shape of the curve exactly. Even the kinks in the curve are exactly the same. So it's not just that the data has random errors where it would just be off. It's systematically offset by a certain amount.
Yeah.
Is that not straight? Is that not something that can be used in the training? If you have a systematic error like that?
Yeah, okay, so here it turned out to be systematic error, but we had also other cases, for example, aluminum, where this was not the case, and it was not like a case like this. So this is data specific, yeah. Yeah, what this means is that there's a shift, right? Is that we can basically train at just one or a few temperatures, and we can already correct for all temperatures. So this is more like an implication. So it's hard to decipher this, what is the reason, right? Because the data sets are constructed in different ways and so forth, but the training was exactly the same, so yeah. Okay, so, but in any case, whether the shape be different or the same, it's not the point. The point is that we can reproduce, of course, the target properties. What is interesting is to look at the out-of-target properties, right? What happens to now, let's say, phonon density of states or phonon dispersion curves when we do this combined training, right? And what we saw is that you can actually, if you combine these two, you basically get almost similar result as with pure training on DFT. And basically all of this gives you the same thing. And if you look at the properties that are in the liquid state, so different thermodynamic phase, and we look at some other properties like structural properties, we can see that they have a good match to, especially for structural properties like radial distribution function has very good match, and we don't see any kind of difference between these models. So it's kind of like it's defaulting back to the kind of solution that you would have with just pure simulation data. But in diffusion, for example, we get actually improvement, which is kind of like surprising for us. We just wanted to check that we are not making other properties worse. What it turned out to be is either we are not modifying them or we are improving on them. So it's kind of surprising that, you know, mechanical properties at the solid state has something to do with the diffusion in the liquid state. So yeah, so this was kind of surprising to us that we could actually improve on this and get a better fit to experimental results. All right, so now I want to show you another way that you can maybe combine the simulation and experimental data, and that has to do with implicit solvent models. So implicit solvent models are very interesting for us for many different kind of applications, like peptide self-assembly that we want to look at, but you can also do it like drug binding if you want in this kind of groups, or protein folding, or any kind of applications like this, right? What is common to all of these applications is that in these simulations, most of the computational effort is spent on simulating the solvent, and typically we are not actually interested in simulating the solvent or the solvent behavior. So what is a natural then solution here is then to just coarse grain out the solvent degrees of freedom, right? And then to use so-called implicit solvent models. You don't explicitly model the solvent, right? Which for all of these applications would probably be some kind of water kind of solvent. Okay, the problem is that when you construct coarse-grained kind of models, you typically need more data because the nature of the problem is not exactly the same because it's not one-to-one mapping. And that means that typically one has to resort to many kind of different approximations. So typically, like I said, when constructing coarse-grained models, you typically have to resort to classical force field, atomistic force field for your data, which has limitations, known limitations, right? Good. So what we wanted to do is we wanted to avoid that and come up with a different approach that you could get implicit solvent models, right? And this is something that we call this resolve, or solvation free energy path reweighting. So here we are combining this data in different kind of ways, and that we are training the model in two stages. We are first training it on the DFT database of small drug-like molecules in vacuum. And this database, so here we use QM7X, but there are many kind of data sets available like this, like SPICE or something else. So there's every year a bigger and better data sets, right? What these data sets have in common is that there's most of the data is for molecules in vacuum. So this is something that for DFT, it's easy to compute, right? So we have this available data set and we can reuse it, right? So this gives us a model for molecules in vacuum. And then we can use experimental data in the second stage. And what we are using here is data that is solvation-free energy data or hydration-free energy for water. So, and hydration-free energy is basically a free energy of transferring a molecule from vacuum to solvent, or to water in the case of hydration-free energy. And we have experimental data for in the same chemical space as this QM7X for this roughly 500 molecules, right? And we can use this in order to parameterize another model. So basically perturb the one model in vacuum to from here get another model in solvent. And we train it by such that this free energy difference between the two models will match our experimental value. And this, basically by training this second model then will give us a molecular model in implicit solvent. Okay. Yeah.
Is this done with the technique that you described before, where you want to simulate, so it is non-differentiable simulation reweighting?
Exactly. Yeah. So we are training on free energies, as you know, like free energies also require quite a lot of sampling, right? There's a reason why for 50 years people were developing free energy estimation methods. Yeah, okay, this is in implicit solvent, so it makes everything faster and cheaper. That's why it's probably doable. In explicit solvent, this would probably not be doable, or not in terms of chemical space. It will be harder. But implicit solvent, you can do this, right? Because you need to predict hydration-free energy several times for several molecules in training. Good. So this approach, kind of combining this, basically avoids us to resort to approximations, right? We don't have to go to classical force fields. We don't have to go to DFT-based implicit solvent. And we don't have this problem with DFT and explicit water, where you have problems that you don't really have problems with bulk conditions, because you never really see the bulk conditions, because it's just hard for DFT. Good. So what can we show with this model? So some results. So we tested then this on what is then the prediction of solvation or hydration-free energy for the molecules that we did not see in training. So for the test case molecules, and we know the same for the same exact molecules, we can also predict them and compare them with classical force fields. And these are our results. So this is just a parity plot, but maybe more important, like in the errors that we are getting. So our results are around 0.6 kilocalories per mole. And you can see that this is much lower than classical force fields. So if you would be doing training based on classical force fields, you can at best be as good as this, right? Because you cannot really exceed this accuracy, right? So with our approach, we can actually be better than classical atomistic force fields. Okay, so if you want visual representation, so what we are able to do now, we are able to push these coarse-grained models to a higher level of accuracy than classical atomistic models in explicit solvent. So we are faster and more accurate, both at the same time. Of course, this is also only for like hydration-free energies, and also only for small molecules. So one needs to extend this, right? But nevertheless, this shows us that this is possible, right? So, and so we are very excited by this. And by the way, so if you would do classical implicit solvent models, these were notoriously bad. So for the same kind of database, you would get errors of around 3.5 kilocalories per mole. So a lot higher, right? Whereas we are almost at the experimental uncertainty. Okay, yeah.
I think what is super cool about this plot is that you actually managed to remove basically the outliers, which arguably are what could hurt you the most in a real project. Do you have an idea of why those outliers are there? Like what went wrong in the classical force fields and what got corrected with the machine learning one?
Yeah, that would be nice. Yeah, but yeah, so it's known that it's very hard to predict these very negative hydration-free energies. Why really this is the case, it's really hard to speculate. So I think we would have to this is, I guess, the downside of machine learning, that so it's very hard to get an interpretable machine learning. So we try to analyze it a bit, but yeah, I wouldn't really put too much weight on that. Yeah, we are postulating something that would not put my, yeah, for sure, I wouldn't say that though. Okay, so of course, one can also like improve on these models, right? So one can use DFT data set to improve on models and construct a atomistic kind of machine learning potential and to push those models up, right? And then we can compare with those. So that was actually at the same time as we published this paper was another paper from Gabor, and they did for machine learning potential in explicit water, tested for 6 molecules in the same data set. They tested the hydration free energy. Okay, and so here you can see the predictions that are ours experiments and theirs with explicit solvent machine learning potential. And actually, we are better on almost all cases except one. It's an unfair comparison because some of the molecules were in our training data. And it's 5 molecules, 6 molecules, so it's statistically not relevant. So let's just say we are on the same accuracy, okay? But with respect to computational cost, this is something that we can say something about, right? And what we measured is something like 4 orders of magnitude to speed up, right? There's a reason why they only tested 6 molecules and not, 500 or 600 that you have in the database. And that is because this is extremely computationally expensive. Whereas we do this in training. So, yeah. Good. So I think I think this opens up the possibility to, at least in the future, do some kind of big scale, kind of implicit solvent simulations that are also accurate. Okay, with that, I want to move to another part, which is going large. So how do we go to 1 million atoms? That is a big promise of these machine learning potentials. So first, I want to say something about our software. So recently, we published this chemtrain framework, and it's a software to train machine learning potentials. So I do a bit of a commercial here. If you are interested in training these machine learning potentials, you can use our software. What is special about it is that you can easily combine different kinds of training, right? Typically, the software that is available out there supports this training based on simulation data, but we make it really easy to combine this with experimental data and do different kind of training loops, or to do like different kind of losses, like relative entropy minimization that is very useful for coarse-grained models, etc. Right? It's based on JAX, and so you can use all the proportionality of JAX, like automatic differentiation, parallelized training, and optimized compilation, and etc. Okay, and also we can use JAX-MD, and you can use this to train as well as to deploy your models. But this has a limitation in that it's not parallelizable across multiple GPUs when you train the simulations. That's why we then did very recently, like a week ago, together with Weilong, chemtrain deploy, which is used as an extension of our chemtrain. And it is used to connect our models and run them in classical MD software. Okay. This has several different benefits. So we first connected it to lumps. So that means that now you can, train your model in JAX or in our package if you want, and then you can export it, and then you can run it in lumps. And it means that you can run all sorts of simulations that are standard in classical MD software, right? If you look at JAX-MD, it's a basic functionality. You cannot run, things that were developed for a lot of years. You want to run it in external field. You want to run kind of bias simulations or something like this, For all of this, you would have to re-implement it in JAX-MD, and this is not something that, why do it if it has been already done and extensively tested, in another package. So we see the usability great if you connect it to some external software. And also, this gives us a parallelization routine, right, that we can exploit from LAMPs. So what we made and what is special, so other plugins to LAMPs already exist, but what is special about this chemtrain deploy is that it's model agnostic. So now you can do any JAX semi-local machine learning potential, right? And you can run it in LAMPs. And this is what is special. And this is what makes it useful, right? Because architectures are changing on a yearly basis for this machine learning potential. So, if you do a plugin for today's model, it will not be useful in a year. So what we did is something that is model agnostic. Okay, so plan for the future. And like I said, it's parallelizable across multiple GPUs. And this actually makes it possible to run 1 million atom simulations. and it's super easy to use in labs, like 3 lines of code. So we tested this software on different kind of state-of-the-art current architectures for machine learning potentials and different kind of systems in order to give people and also to us some frame of reference, like which architecture for which kind of system and what can you actually do. So that we have an idea in the head what's possible now. So we tested Allegro, Maze, and Pain. These are all equivariant graph neural networks, but they are different, right? Allegro is strictly local model, no message passing steps. Maze and Pain have message passing steps, but they do it differently. So Maze has some attention mechanism there. Pain is like more like lightweight, it's supposed to be, and so forth. So there are architecturally, there are differences between them, but they are, let's say, go-to models these days for machine learning potentials, and as well as other property prediction for molecules. And then we tested this on 3 different systems. One is a solid state aluminum, so it's supposed to target material science. Then it's like a replicated chignolin in water. So this is supposedly targeting any bio kind of physical simulation. And then just to test 3D and 2D systems, we also did a water slab. Okay. So first of all, why do you need multiple GPUs and parallelizability across GPUs? Is that if you just use one GPU, you would run out of memory. Now, this will depend on a particular model, right? What we did in order to test these models on the same kind of level is that on these 3 databases, we try to train them to the same accuracy. And so we fix the architecture and the hyperparameters so that they are approximately the same accurate. And then we test computational cost, okay, and memory cost, okay? And so, but roughly, right, for this kind of systems, even if you strip down the model very much, you cannot go beyond 500,000 atoms. At certain point, you will run out of memory, right? And this is on A100s. Okay, if you want to H100s and 98 gigabytes, you can add some 100,000 atoms, but not much more, right? So that's why if you really want to do large scale million atom simulations, you need multiple GPUs, and then you need something that is parallelizable across multiple GPUs, and standard software to run MD simulations is not. Okay, and that's also something that we are very proud of, so that we can now really deploy this on high performance computing clusters, right? So now you see the strong scaling results for these 3, this aluminum, chignolin, water, these 3 systems for million atom simulations. And yeah, so in order to explain this, and also for aluminum, you can see the reference to classical potential. So this is the MEAM, which is typically used for metal simulations or for like a material science. So you can see that all of it is, so we are, of course, computationally more costly than classical force fields. Right? This is a given because we're using a graph neural network, right? Then the next thing that you can notice is that pain is missing from this chignolin and water case, and that is because in order to get it the same accuracy, we noticed that the architecture has to be increased quite a lot, and then we are just in 64 atoms, we could not get it to 1 million atoms. So you're just running out of memory. You would need more than 64 GPUs to get to 1 million atoms. So pain, from our experience, right, and these limited kind of test cases seems to be too memory intensive. Then Allegro, which is strictly local, right, it's super parallelizable. It has almost, I'm not showing you here, but the efficiency is almost like 100%. It's super parallelizable, and that is because it's strictly local model, meaning there are no message passing steps in between, and this has an implication, direct implication in terms of the scaling, right? So we came up with this formula how to compute the parallelization speed up, and our results are basically on top of this curve, right? And you can see that how much you can speed up your simulation based on the number of processors that you use, or the number of GPUs, and this will depend on the cutoff that you are using, as well as this is R, as well as on the T, these are the number of message passing steps that you have. So if you go to large message passing steps, you will, significantly decrease computational efficiency of your model. Okay, so because in Allegro you don't have this message passing steps, you have super good parallelization, super good scalability. And that's why it behaves like it performs the best here in aluminum and in the water case. If you go to more complex chemical space, it turns out that you have to increase the architecture of the Allegro so much that actually then the message passing steps models like MACE are actually more computationally efficient, but with the low amount of message passing steps, like 2, I think we use here. Good, so this is for us was very useful information for our future applications to know, which model to use in what kind of reference, right? Do you just want to use like 100 atoms or like 100,000 atoms, or do you want to really want 2 million atoms, and which model you should pick, right? And what are the plus and minuses of these different models? Yeah, if you want to use these models, have a look at our links, and we published all of this, and we have, I think, quite a nice documentation, and so you can get started with this different kind of training routines. Good. Great. So now coming to the third part of my talk. So this is about tackling long-range interactions, and we tackle this using a hybrid model. So combining physics-based models with graph neural networks. So there are, this is, I would say, very active area of research. There are many different kind of ways that people go about this. Some like make it like a global node and a global kind of information, try to do it in Fourier space or things like this. So we try to model it from a physics point of view to try to model long-range interactions, specifically electrostatic interactions, by combining with a physics-based model. And critically, we don't really want to compromise on computational efficiency, right? So, like I said, is that typically a cutoff for any kind of graph neural network is around 0.5 nanometers. So this is very short in terms of electrostatic interactions that decay very slowly. So something you need to, if you have a large electrostatic interactions in your system, like charge systems, you need to do something about this. Otherwise, you're just going to be not correct. At the other end, right, you want to reuse the strictly local graph neural network because they have great scalability, right? And like I showed you before, right, they just scale super nice. But of course, because they are strictly local, they cannot model anything beyond this 0.5 nanometers, for example. And like I said, you don't want to increase the cutoff, right, because this would also make your computational model computationally inefficient, or increase the message passing steps in case of graph networks. So what we did is this CHELI, which is a charge equilibration layer for long-range interactions, is that we combine a physics-based model, which is charge equilibration method, that has been around for quite some time. It's typically used in React's force field, if you know it. It's about for reactive molecular dynamics. It's a classical force field. And what it does is charge equilibration method is a method which distributes partial charges by minimizing the electrostatic interaction. So you are minimizing this interaction, which is basically Coulomb interaction with Gaussian charges. Okay, and you minimize this the total electrostatic energy. So you assign partial charges in this way. And then you can, of course, compute electrostatic interactions from these Coulomb interactions. Now, how it was done classically is that these parameters of this model, this J's here, which are the hardness, or this electronegativities here, they will be parameterized based on DFT, simple DFT calculations, and they are species-wise only parameterization. So what you can do is now with machine learning, you can parameterize it, of course, with a machine learning model. And what you can do is you can integrate this within your graph neural network. So here you can see how we can integrate this classical method within a graph neural network. So here is, for example, of Allegro. So Allegro would take as an input R, which is particle 3D coordinates, Z, which is type of chemical element that you have, and N is the connectivity of your graph, which is based on your cutoff. And then you have some embedding layers and then some interaction layers. And then you can basically embed this layer basically in between. Okay, so you can get, yeah.
Yeah, so I just wanted to, you have to quadratic scale the number of particles here, right?
Yeah.
And so how does this address, so a lot of the alternative work out there is simply trying to alleviate the scale, like getting like a zero sum type scaling, like not in or linear scaling. So do you foresee any problems with this, or do you think that the primary problem with machine learning architectures is that the memory overhead of attention on the pattern is the main innovation?
Yeah, okay, so here you can postulate this as a linear equation, a system of equations, yeah. But there are also solvents already existing that solve this in n log n, I think. So there's, like I said, this charge equilibration method, it's an old method. And people have figured out how to do this efficiently, how to solve this efficiently, and how to also, this already implemented in LUMS. So you can just use it. Yeah. So there are solvers for that, yeah. So it's, I will show you the overhead, and the overhead is minimal to the baseline model, right? Which is super expensive. So anything you add on top is like almost no cost. Okay, so what we can do that was not possible before is that you can, these parameters like this hardness and electronegativity, you can now make it environment dependent, and this environment dependence basically comes from your graph neural network. The same thing as, you know, interactions are environment dependent if you look at them, and then you can reuse this in order to also predict these parameters, right? And then what you can do is you can loop this back, right? So this charge equilibration method will predict partial charges, but this is a global method, right? And then we'll give you back the partial charges in each particle, and then you can embed these charges as well as the charge environment back to your graph neural network, right? So here in the charge embedding, and then this will give you the global information back to your model, back to your local model, okay? And so it's here you inform basically your local interactions about the global system, or information of the global system. And then, yeah, this you can then update your, here in Allegro, this edge features. Good. So yeah, this is what I said. So the charge can also be environment dependent, right? Good. So we tested this on this benchmark systems that were actually done by Baylor. So these are the 4 systems that are typically referenced for long-range interactions. So I'm not going to go through all of them because maybe it's not so useful, but just maybe one to give you an idea how this long-range plays along. So, for example, in these carbon chains, right, there are 10 carbons in a row, and then you can have hydrogens at the end. And you have, let's say, these 2 different systems. These are just 2 different inputs to the machine learning model, right? So in one case, you have 1 hydrogen atom, and in the other case, you have 2 hydrogen atoms at the end, right? And the problem is this, is that in the local models, right, when you predict the interactions here, you can never, because it's local, you will never see that there is a difference at the end, okay? So in your cutoff, you would maybe see a few of these carbons, okay? And then you would not see the end. So you will never be able to distinguish between these 2 kind of states. And you can see that the partial charges on each atoms are nevertheless very different. So not just in the vicinity where we have difference in how many hydrogens I have, but all the way on the other end of the chain, I have different partial charge as an effect. And this is a long-range charge transfer effect, okay? So if you have a strictly local model, by theory, you by default, you cannot do this, right? Okay, you can never see this because the input is always the same, okay? And then there are other like test cases, right? So we tested this. So we took Allegro as our baseline model, and then we just add this our Celli interaction layer. And in one case, we are learning the hardness. This is this case, second case, and in one case, we are not learning it, but taking it as a reference parameters. So in short, right, we can achieve better results, right? We have lower errors compared to the other strictly local models tested on the same kind of systems. What we also looked at more chemically diverse systems, because all of these systems are just chemically very constrained, right? They're just test case systems. But we also trained it against the OS62 database, where we could also show some improvement. And this is basically just because a lot of the other methods, for example, in this EWALD or newer neural P3M methods that are also trying to tackle long-range interactions, they were tested on these data sets. So we try to see where we are. So in general, right, we can see that we can get a slight improvement with respect if we add these long-range interactions. But I would say that in general, OS62 is maybe not the best data set to test long-range interactions, right? And also we can show that just by increasing the model architecture, you cannot get the same kind of results. So if we add Chelly, so this SL, this is how much you increase the architecture of the model. So the more you increase it, of course, you can reduce these errors lower and lower, right? But with Chelly, we can always beat the reference model. Good. And just to show that our Chelly is rather model agnostic, right? It's just a layer that you plug in between. So you can plug it into any kind of graph neural network. And so we also tested it with Maze, and we can also see the improvement with respect to the energies especially for these root mean square errors. Good, and now for the computational cost, right? It much more matters the parameters of the architecture and which graph neural network that it does to add this layer or not add it, right? So you can see here the baseline models in full lines, and this is a time per structure, and the reference addition to the Chelly. So if we add Chelly, we have a slight overhead in computational cost, but this is nothing compared to the differences between different architectures. And so, for example, if you go to DimeNet, which also has a explicit three-body input, then this can scale up blow up significantly more. What I'm saying is anything physics-based that you add to the graph neural network is going to be insignificant computation cost. Yeah.
So, but in this Chelly architecture, you have a sum over all pairs, right? But scaling looks very linear, the number of atoms. Why is that? Why is it not critical?
This is all super low. And as I said, this computational cost is dominated by the graph neural network and not the Chelly.
Scaling large systems, scaling you to the graphic scaling at some point.
No, I mean, we expect linear scaling with the system size just because of the graph neural network.
Yeah.
So, like I said, so the scaling, the time per, and also you cannot really determine the scaling with the number of atoms that you see, 200s, it's not really scaling, To do the scaling, you would have to go to 1,000 and so on. So it's not a really scaling plot, right? This was just, we wanted to show that the difference with respect to the architecture is much larger than it is adding or not adding this Chelly layer. It's basically the same. So the computational overhead is negligible in that sense.
But it seems like there is a size-dependent scaling, right? It seems because the scaling is not a constant factor on all the different. So there's an overhead. The question is whether this is linear arbitrary.
Yeah, exactly. That's my mind.
Yeah. Okay.
Yeah. So here the scaling will then be quadratic, just because we did not use this linear solver for this charge equilibration scheme. Yeah, but there are schemes like that we just didn't implement it. This was done in JaxMD and it's not implemented. So, but we can use it and we can implement it, the better scaling, the routines for that. We just didn't do it. Yeah. Good. And now for the last part, I want to say something about going from training, from parameterization to inference, and especially how to do this in a Bayesian kind of sense. So we try to see if we can get uncertainty quantification and if we can get it from Bayesian kind of methods. So that being that Bayesian methods are very mathematically rigorously founded, right? And we wanted to see if we can do this, right? For like very complex models like graph neural networks and quite large data sets, like millions of structures and points, right? Which is computationally expensive. So that's why we basically used, let's say, scalable Bayesian methods. And I will show you what is the trick and how to do this. Okay, so typically you would do Bayesian inference by using some kind of Markov chain Monte Carlo methods, with the gold standard being Hamiltonian Monte Carlo method. And this is the method. It's not really important. The important part is that in Markov chain Monte Carlo methods, the likelihood that you need to compute is computed on the full data set. Now, what you can do is in order to make these methods applicable to large models and large data sets, you can do the same trick as you would naturally do in machine learning, right? In machine learning, we don't do gradient descent, we do the stochastic gradient descent. So what you can do is, instead of computing the likelihood on the full data set, you can compute it on a mini batch, and this gives you a whole family of methods, and one of them being stochastic gradient longevity dynamics. So this was not developed by us, but we wanted to see if these methods would actually work for machine learning potentials. We first did it on the benchmark toy case. It's just like linear Jones potential and data coming from the minimum well. And we wanted to see how we are predicting outside of this minimum well, which, you know, the predictions are in mean is in blue, and it's different than the true, which is in black, obviously, because we have no data there, so we cannot really generalize. But we wanted to see whether or not within 1 sigma or 2 sigma we can capture this difference, right? And this would be the signal that our method is working well, and that we can actually match and get similar results as, say, gold standard Hamiltonian Monte Carlo. And we can, and this works rather well. And then we can also go and do this for actual graph neural networks and actual large data sets. So here we apply this to coarse-grained model of water. And here we don't have a reference anymore, so we don't know the truth, but we can get some physical intuition and see if it makes sense what we are predicting, right? So we train this coarse-grained model at a specific temperature, and then we would expect that this model would be correct and very certain of the predictions at this temperature, but not in other temperatures, right? And this is exactly what we get. So you can see that the predictions match the reference super well, where we have the training data at the same temperature, and the uncertainty is so small you don't see it. When you go to different temperatures, right, you can see that you deviate from the truth, but more importantly, you are within this 2 sigma, you capture this error. And this is what we wanted to see, right? The same thing here for the density with respect to temperatures, where you have the data, you of course are on the line and you match the reference, but then the more you deviate in terms of temperature, the more you deviate from the ground truth, but you are able to capture this within your 2 sigma interval. Okay, I will just stop here and just say that we also develop a software here, stochastic gradient Monte Carlo, to implement all of these different methods in checks. And this is actually application agnostic, so you can use it for machine learning potential, but also for any other kind of machine learning model that has to do with complex models and large data sets. And you can do Bayesian kind of inference of these machine learning models with this software. Okay, with that, I just want to conclude and say that, yeah, we are working on these machine learning potentials that hold a lot of promise. Of course, there are certain things that we still have to improve. I would say that data is the main part, right? That these models hinge on the good data, and we try to overcome this by using different kind of data sources, by using uncertainty quantification, using active learning, and so forth. And that we also are working on models that will actually be used 10 years along the line. And for that reason, we look at models that are really good in computational aspects. And for that reason, we look at how to develop software that will enable us to use these models for actual applications, and also look at architectures which are cost effective. Thank you very much for your attention.